Hello, welcome to another presentation. Now this time on the rather contentious subject of gravity is really density. Ooh, I think I'm going to open a can of worms with this one, but there we go. I'm just going to hit it with physics and mathematics and see where we go. So these images, love them, brilliant. We've got this wonderful old German painting, wood engraving of Newton's famous steps under the apple tree, the famous event which probably never happened, about him debating the forces that when the apple fell off a tree, that could be the same forces that govern the motions of the planets, so-called, around the universe. And then we have a Wikipedia here. This was voted apparently the best image of the year, or along those lines of the shape of two massive galaxies in the picture are distorted due to gravity. Right, okay. The Hubble image is a composite of data, so put data together taken from three separate filters on wavelengths of ultraviolet, blue and red portions of a spectrum. Okay, so basically it's kind of CGI'd. That's what they're telling you. Anyway, without getting too controversial again, let's move on. There are two types of gravity to start off with. Immediately start off with that. There's not just gravity on Earth, there's the gravity that we'll look at, the universal one. The first one we're all aware of, we should be, the standard acceleration of gravity or standard acceleration of free fall, often called simply standard gravity and denoted by g0 or gn, is the nominal gravitational acceleration of an object in a vacuum, interesting, near the surface of the Earth. It is a constant defined by standard as 9.80665 meters per second squared. And for those of you who don't use SI, it's about 32.17405 feet per square second. Wikipedia the source, so I always tend to go to Wikipedia. It's a good base source to start off with. The two types of gravity. So acceleration due to gravity g, little g, is 9.81 meters per second squared. There we go in scientific notation. Newton's second law, F equals ma. I've done a separate video about that. It's actually a law, but it doesn't always apply because F equals the rate of change of momentum, but I'm diverting. The weight is mass times gravity. The mass is measured in kilograms, the weight is measured in newtons. Either capital N or Newton's lowercase because it's named after someone. But the units are kilogram meter per second squared. That is little g. Big G, the gravitational constant, is big G is 6.67430 to 15 decimal places precision, allegedly, times 10 to the minus 11 Newton times meter squared times kilogram to the minus 2. So that's not the same as this one. So these units are not the same as that either. Newton's law of universal gravitation, F equals g mm over r squared, very famous one. The product of the masses of the planets divided by the square of the distance between them, the inverse square law. So they make these two equations equal, mg, you make it equal to this one that's here, mg equals g mm over r squared, little m cancels, little g is gm over r squared, or big G is g r squared over m. That's if you make these assumptions that this value is correct and the assumption that they are both equal. Here's a great one. I love a graph with more than two axes. You've got the axes here going in terms of g, and the units here are good old SI base units. 6.671 up to 6.676, and then you have on the left axis you've got the people who were doing the discoveries. On the right axis you've got the years from 1982 to 2014, and then you've got the range of data. So the precision, you've got these points here, and with never trust a graph that is scaled, so you either scale so you can't see uncertainty bars or they're not included. So you see a range of uncertainty values, so that's a value, but it could be from there to there on that axis. So as we see, it's ranged from 6.672 here, the biggest value is there, the smallest value is here, and a range of uncertainties depending upon what type of experiment they did. So time of swing, angular acceleration, servo, beam balance, two pendulums, atomic interference. But it is a very, very small number, 10 to the minus 11. So it's always good to compare big G with the electrostatic force. The Coulomb constant, the electrostatic constant, is 1 over 4 pi epsilon naught, which is 8.987551792 to 14 decimal places times 10 to the 9, a huge number. Normally rounded up, easy to remember, 9 times 10 to the 9, Newton metre squared per Coulomb squared. If I do a ratio now and divide big G by K electric, and I'm just looking for the magnitude, 6.67430 to the same number of significant figures, 10 to the minus 11 divided by 10 to the 9 ends up with 7.4262 times 10 to the minus 21. So, what does that mean? Well, G is 0.000000000 all the way through here, 7 times weaker than the electrostatic force. You can measure this one easy, G you can't. And apparently a Nobel Prize is waiting for someone who can measure this accurately. I'm not surprised, it's such a small number. It's the force, gravitational force, which is the hardest one to reconcile with the strong force, weak force and the electrostatic force. And I wonder why. Let's move on to pressure and density. So pressure is force per unit area, which is in terms of SI, newtons per metre squared, and density rho is mass per volume, kilograms per metre cubed. Get these into base units, kilogram metre squared, kilogram metre per second squared, metre to minus 2, and then those tidy up from there to there. And then if you multiply, it's a neat little trick, if you multiply top and bottom of force by distance, so it doesn't matter because these are going to cancel, but if you do that, then you have force times the length, force times distance, which is energy, and area times volume, area times length, which is volume. So you end up with the units of pressure being a joule per metre cubed. So pressure is measured in terms of joules per metre cubed, and density is measured in terms of kilogram per metre cubed. Isn't that an interesting comparison? The Bernoulli equation, quite a famous one, where you have P0, which is your pressure, equals P1 plus rho GH plus half rho V squared. It's very much like a kinetic energy equation here, and this is an image from a great website called Hyperphysics, and it's really good for just having a look at how you can images here, the velocities going in, and this is conservation of energy, energy equal before equals energy after, and then you've got this narrowing here, you've got a smaller area, so A2 here is less than A1 here, the volume 2 here, the velocity here is greater than V1, so the pressure here is lower. And that's what makes why aircraft can fly, because it's all down to the shape of the wings. So it's just an interesting factor there, but let's get into it. Dropping an apple. I thought I'd choose an apple because an apple is very relevant as we're talking about Isaac Newton. So gravitational potential energy is mg delta h. It's mass times gravitational acceleration times the change in height. And the kinetic energy Ke is 1/2 times the mass times the speed squared. What are my assumptions? Here's the Earth, here's the apple. My assumptions are the apple has a density of 750 kilograms per meter cubed. An apple's density is clearly more than the density of the air, which is a measurable value, 1.225 kilograms per meter cubed. So that's less than that. But an apple's density is less than the density of water. The density of water is nearly 1,000 kilograms per meter cubed. That is obviously less, which means that is going to float. Air resistance is negligible. Atmospheric pressure is constant at sea level with a value of 101,325 pascals. It's 1.01 times 10 to the 5 newtons per meter squared. Temperature is constant at 15 degrees centigrade. And the density of air is constant for its height. I'm going to do heights up to 200 meters. And this is just a standard kinetic energy. When you drop something, you've got potential energy here, and it converts into kinetic energy. So your GPE is mg delta h. Your kinetic energy is 1/2 mv squared. What it loses in gravitational potential energy, it gains in kinetic energy. So you make these two equal to each other. Mg delta h equals 1/2 mv squared. The m's cancel, and you end up with v equals root 2 g delta h. There we go, v equals root 2 g h. I've done a spreadsheet here with different values, and I put the titles here to make it simple. G in quotation marks, otherwise it defaults to being capital G, and these are values that are given by Wikipedia, 9.80665 to 9.80665, doing theoretical value of V, an altitude from 10 meters to 200 meters, 2 times G times H, which gives you that. You can check those out. And then V is the square root of that, which is in this equation, and they're getting 14 to 62.63, which makes sense. Always look at the values and go, do they make sense? If I drop something from 10 meters, it's going to reach a speed of 14 meters per second, which seems about right. If I'm dropping it for 200 meters, it's going to reach a speed of 4 or 5 times that, which again seems right. Not the other way around. If it was the other way around, I've done a calculation mistake. So the Bernoulli equation, P equals P0 plus rho GH plus 1/2 rho V squared. I'm looking at the potential energy per unit volume, which is rho GH. Kinetic energy per unit volume is 1/2 rho V squared. Similarity with the kinetic one we just done. Same assumptions. I'm doing the same here, that I'm saying that I'm going to lose what I lose in potential energy. I'm going to gain in kinetic energy, so I make these two equations equivalent to each other. Instead of masses cancelling, this time the density cancels, and you end up, as you expect, with getting the same equation, V equals root 2GH. No surprise there. Happy days, it all works. Now, let's have a look at this. So we're looking at potential energy. So we've got potential energy here. The arrow's here. It's not moving. I've just left it in there. You know it's going to go down. It's not moving. It's kept up here. So I have the difference. I've moved P1 over there. So it's P0 plus P1 is rho GH, and it's at the top here before I let go. So there's no kinetic energy. I'm going purely by potential energy. If I rearrange it in terms of G, I then with P0 minus P1 divided by rho H. Equation 1. Using a equation of motion, V squared equals U squared plus 2AS. If I leave it at the top of that trajectory, and it has an initial speed of 0 meters per second, acceleration is G meters per second squared, and the S is H meters. V squared equals 0 squared plus 2GH. We then get this, rearrange it in terms of G, V squared over 2H, equation 2. Double check the units. G is measured in meters per second squared, V squared is meters per second, that's all squared. H is measured in meters, that squares everything, meter cancels that one, meters per second squared. Happy days, equation balances. Always worth checking the units to make sure that's at least right. But you see, checking units does not factor in a numerical value like 2, because 2 does not have a unit, it is purely a number. No. Equation 1, G equals this, P0 minus P1 over rho H. Equation 2, G equals V squared over 2H. The G's are the same, therefore they are equal. So when you make them equal, you go a little bit of mathematical rearranging. You've got rho H here, H here. The H's are common to both sides, they disappear. So V squared equals 2 comes up here, times P0 minus P1 divided by the density, and then of course you just take the square root. So V equals root 2 P0 minus P1 over rho the density. And again, that's equation number 3, and I'm just going to do a quick unit analysis. The unit analysis of V, that's meters per second. 2 doesn't have units. I'm just going to use one of the pressures because they have the same units. So newtons per meter squared. Rho is in units of kilograms per meter cubed. This square root is just replaced by the power half, makes it look a bit easier to work through. Newton is a kilogram meter per second squared times a meter per meter squared, meter to the minus 2, divided by kilograms meter to the minus 3. Tidy up, kilograms disappear, common to both. Meter to the 1, meter to the minus 2 becomes meter to the minus 1, s to minus 2 there, meter to the minus 3 there. And then that meter to the minus 3 comes up on top, becomes meter to the plus 3 minus 1 becomes 2, s to minus 2, there we go. And then I'll just multiply by using the power law. 2 times a half is 1, minus 2 times a half is minus 1, meters per second equals meters per second. Happy days. The equation balances. It checks the units, but again it doesn't confirm whether or not there should be a number there, because a number has no units. This is a neat website, really neat one. It's going to be in the links. So you've got these links here, so you can play about with it. And I'd just like to go for the extreme. So for example, calculate the altitude from air pressure, and then calculate the air pressure altitude. So what I did first was I put the altitude of 200 meters, the extreme, and it gave me an air pressure of 98945.33, and then I then put that into there, calculated it, and it came up with the altitude. So I'm double checking, yep, that those values match. It's a great website. So my calculated value of G, using equation 1 of P0 minus P1 divided by the product of density times height, altitude, and I've used that value here. I've just highlighted the value from the page before. I've done the altitude from 10 meters to 200 meters across the board to make it comparable. And then I've gone all the way through in the spreadsheet carefully, because I always do it bit by bit. Density, P0, P1, P0 minus P1, H, rho times H, and G, which is P0 minus P1, divided by these two. And look at that, 9.8 all the way down to 9.71. That's nearly 9.81, which is the established value of the acceleration due to so-called gravity. So by using values of pressure, density and height, all of which are independent of gravity, pressure is measured in force per unit area, density is measured in kilograms per meter cubed, and height is measured in meters. All these can be measured independently. We've got a value of G depending upon pressure and density from 9.8 down to 9.71. So G is higher, the value of G is slightly higher the lower you are. So the further you get away from the surface of the Earth, the G value decreases, which seems reasonable. Okay, so it's starting to really make some sense here. This is measured in terms of meters per second squared, of course. Let's look at equation number 3. So can we calculate the velocity? Yes, we can, because the square root of 2 P0 minus P1 over rho. So doing the same thing, altitude from 10 to 200 meters, all of the spreadsheet values, P0 minus P1, 2 times that, divided by density, and V is the square root of that, and I get values from 14 to 62.33. Interesting. Because when we go to this page, I've just screenshot the altitude from 10 to 200 meters, the theoretical value of the square root of 2gh, which is 14 to 62.63. The velocity calculations using pressure and density gives 14 to 62.33, and they're virtually identical, order of magnitude, and very, very close. So that's the first stage, and then the acceleration from h of 10 meters to 200 meters, and g from the standard value as given by Wikipedia of 9.80665, same value, meters per second squared. My acceleration calculations based on pressure divided by density times the distance in units of meters per second squared. Oh look, 9.8, 9.71. So decreasing as you're going up with height. There you go. So it's not only is it the right order of magnitude and pretty bang on, it shows it as a change in G, in little g. So I said before, the apple has a density of 750 kilograms per meter cubed. It's more dense than air, because air is only 1.225, but it's much less dense than water, so the apple is going to float. It's really obvious. If you put a brick on the water, it sinks. If you put a massive ship weighing thousands of tons, it floats, because its relative density, it's got a massive hold. With air, its relative density is less than that of water. Again, the same values. And this time, just for a little bit of fun, I've gone from what's it like if you go into water, so minus altitude or whatever, minus altitude lower down. Whether or not it's worth water, I don't know, but minus 200, it gave me a value of here, and then I put that value into there, and it gave me an altitude of minus 200. So I looked at zinc, which has a greater density than water, ignored water resistance, temperature, atmosphere, the same thing, everything constant. And what's really interesting is I can't find anywhere that's got a calculator to do this, because there are issues of fluid flow of it going into water and everything else. I mean, it's quite hard to find one that actually works. But going lower than sea level, So underground, perhaps a good analogy. Lower than underground, going -10 to -200 meters. The pressure goes from 101,325 down to 103,750 to 200 meters. And the velocity of something dropped is going to go increase out. So density, yes, the density of water. So put it into water straight away. So something is going to go from 0.49 to 2.20 meters per second. Now if we compare that with the velocity of something dropped in air, it goes from 14 to 62.33. Now in water, it's going to go 0.49 to 2.20, so a lot slower, which is what you expect because the density of water is 1,000 or so kilograms per meter cubed, which is greater density, relative density, than the density of air, which is only 1 kilogram per meter cubed. So that's my summary, that acceleration due to gravity, as banded about, is that gravity is really, the acceleration is due to density and pressure. So gravity is really density, the acceleration. Big G is a very, very difficult constant, so-called, to calculate because it's based on a lot of assumptions. But little g, acceleration, is due to density and pressure. So that's why my takeaway statement is gravity is really density. Those are references. Thank you for watching. Any comments, likes, please subscribe, and thank you for watching, and take care now. Bye bye.